You've probably all been taught that all matter, all of everything on the entire planet, is composed of atoms. Atoms compose everything and anything. Generally, when you look at mundane things like tape dispensers or pillows, you aren't thinking about the immensely complicated inner workings of the universe. But the atoms of the Earth are in a constant and frenzied state of motion. For example, the atoms in this cat are vibrating furiously as we speak. The atoms in the air we're breathing are bouncing around, shooting around like crazy. If you thought that atoms are hard to visualize because of their minuscule size and incalculable quantities, just wait until we delve into the atom and see what's going on in there. You won't believe how complicated the planet really is. There are three types of particles in an atom. They're called the proton, the neutron, and the electron. The proton and the neutron are super cool and amazing, but we're going to focus on the electron and how it moves around and exists in an atom in this video. Electrons are crazy tiny particles. They're so small that even today in 2015 we can't see them with our highest powered microscopes. I can't give you a point of reference for their size because we just don't know how big an electron is, but I can give you a point of reference for an electron's weight. One electron weighs 9.1 times 10 to the negative 38th power grams. That means that if you had 1 gram that was comprised solely of electrons, you would have approximately 1 billion electrons. It's impossible to visualize or even remotely comprehend the size of an electron, and that's why they're so amazing. Electrons in an atom exist around the nucleus, which is the dense central region of an atom. They exist in areas called orbitals, but before we get too far into orbitals, I need to give you one super fundamentally important fact that you absolutely have to know about orbitals before we go any further. A maximum of 2 electrons can exist in any given orbital. Only 2. Well, there can be one electron in an orbital depending on how many electrons an atom has, but there can never, ever be more than 2 electrons in an orbital. Orbitals are honestly a fairly abstract concept. They don't have definite or constant shapes. Orbitals are really just a collection of points where electrons have been detected. It's like a probability field, or a map of where you're likely to find an electron. Since that is far too complicated to explain or even to comprehend, in this video we're going to act like atoms are structures that actually have constancy and organization. Each atom has specific energy levels on which specific numbers of orbitals exist. A good way to visualize the energy levels of an atom is by thinking of a target. The bullseye here is the nucleus of an atom, and each ring is an energy level. As the rings get larger, the amount of energy required for an electron to exist on that energy level also gets larger, and the number of orbitals that exist on that energy level increase as well. So this ring here requires the least amount of energy for an electron to exist in and contains the fewest orbitals. It also corresponds to what is known as the first energy level of an atom, which makes sense because it's the ring that's closest. You generally number these as like 1, 2, and 3. These energy levels don't go on forever though. The highest number of energy levels ever discovered in an atom is 7. Electrons fail energy levels from the middle out, so they take up the spots that require the least amount of energy first. This demonstrates a very important fact of nature. All matter tries to stay in its lowest possible energy state, which is called its ground state. Matter is inherently lazy, and that's why the energy levels of an atom are filled through the easiest path. One thing you shouldn't forget, however, is that we're dealing with a 3-dimensional structure, so the target analogy isn't entirely accurate since it's drawn in 2 dimensions. So as we continue in this discussion, just keep that in mind when you're visualizing these concepts. I mentioned before that each energy level contains a specific number of orbitals, and that the first energy level contains the fewest orbitals. In fact, the first energy level only contains 1 orbital, and that orbital is called the s orbital. The s orbital is the easiest orbital to analyze. It's shaped like this. It's a simple sphere. It's very easy to imagine and very simple to deal with. If you remember the super important orbital fact I gave you, you'd realize that a maximum of 2 electrons can exist in this s orbital. And since this s orbital is the only orbital on the entire first energy level of an atom, that means that a maximum of 2 electrons, only 2, can exist on the entire first energy level of an atom. One more important fact about s orbitals is that they are present on every energy level of an atom. So there is exactly 1 s orbital on each energy level. The amount of energy required to exist in an s orbital on higher energy levels is obviously higher, but the general concept of the s orbital is the same. The s orbital on the first energy level is called a 1s orbital because it exists on the first energy level of an atom. The next orbital we're going to discuss is called the p orbital. The p orbital requires more energy to exist in than the s orbital. Actually, it requires so much energy to exist in a p orbital that p orbitals can't exist on the first energy level of an atom. So the first p orbitals aren't encountered until you reach the second energy level of an atom. The p orbital has a pretty weird shape. It's something like a dumbbell. Like this. This is a balloon approximation of a p orbital. One crucial thing to remember about p orbitals is that they will always come in groups of 3 on an energy level. You'll never find one lone p orbital like the s orbital, and you'll never find 2. There will always be groups of 3. The 3 p orbitals will be positioned so that there's one parallel to each axis, like you'll see in the picture here. All 3 of those p orbitals won't necessarily be filled, depending on how many electrons an atom has, but they will all be able to be filled. In the same way as the s orbital, there will be 3 p orbitals on every energy level. The p orbitals on the second energy level are called 2p orbitals. 2p, because they exist on the second energy level of an atom. No 1p orbitals will exist because no p orbitals exist on the first energy level of an atom. On the second energy level of an atom, then, there are a total of 4 orbitals. The spherical s orbital takes up 1 spot, and on the second energy level, that s orbital is called a 2s orbital. The 2 indicates the energy level that the orbital is on, and the letter, the s, in this case, indicates which orbital you're talking about. The 3p orbitals take the rest of the spots. So, remembering the super important fact that I told you before, that a maximum of 2 electrons exist in one orbital, we can calculate that of the 4 orbitals on the second energy level, a maximum of 8 electrons can exist on the second energy level of an atom. The third and final orbital we're going to discuss is called the d orbital. As you might expect, this orbital takes even more energy to inhabit than both the s and the p orbitals. It takes so much energy to inhabit that you won't find any d orbitals on the first or second energy levels, and you'll instead encounter your first d orbital on the third energy level. Just like with the s and p orbitals, the d orbitals that you encounter on the third energy level will be called 3d orbitals, because the orbital is on the third energy level and it is a d orbital. On every energy level, there will be 5 d orbitals. Just like there are 3 p orbitals and 1 s orbital, there will always be 5 d orbitals. There can never be any fewer than 5 on a given energy level. The d orbital shape is even weirder than the p orbitals. As you'll see on the board, 4 of the 5 d orbitals are kind of shaped like 4-leaf clovers, but the 5th just goes crazy. After all this weirdness, don't forget the important basic fact that a maximum of 2 electrons can exist in every orbital. Using that fact, let's calculate the total number of electrons that can be held in the third energy level of an atom. So starting from the bottom, we have one s orbital that on the third energy level is called a 3s orbital. So we have a 3s orbital, and there is one of them. And then we have 3p orbitals, and on the third energy level, they're called 3p orbitals. 3p, and there are 3 of them. And finally, we have our 5 new d orbitals, and those are called 3d orbitals as we established before. So adding together the numbers at the bottom, we calculate that there are a total of 9 orbitals on the third energy level, and that means that there is a maximum possibility of 18 electrons to be held on the third energy level of an atom. This video has been an introduction to a concept called valence bond theory. In valence bond theory, physicists have hypothesized that some molecules form mutant orbitals through a process called hybridization in order to bond more effectively with other atoms or molecules. Hybridization looks like a big scary word, but really all it means is that a molecule has taken regular atomic orbitals and mushed them together to create an entirely new form of orbital. For example, an sp-d orbital is obviously a mixture of an s orbital, a p orbital, and a d orbital. So it'll have some s orbital character, and some p orbital character, and some d orbital character. The whole concept of hybrid orbitals and bonding is really, really neat, so if you enjoyed this video, I would highly suggest that you read more about it. Thank you for watching, and I hope you learned a lot.